record. All right. So for the sake of the video, I am going to take a look at our handout for 3.1 and 3.2. We're going to look at some different properties and then see how we can apply exponential functions as well in our daily lives. The first property I want to show is how first and second differences don't help us when it comes to exponential functions. So we have all of these subtractions, and now 8 minus 4 again is a 4. 16 minus 8 is an 8. 32 minus 16 is a 16. It is not constant, just like the first difference. It doesn't help us. The funky thing about exponential functions, we can identify if something is exponential or not by doing a ratio. So take a look at how it's different. I'm not doing subtractions. If you take the y value, divide by the previous, if you take the y value, divide by the previous, if you take the y value and divide by the previous, it gives you a clue of whether this is exponential or not. Yeah, it can give you a clue. So this is first ratios. Sometimes it's not like a guarantee thing where the ratios will help, but it does give you a clue if numbers seem a little bit similar. So let's take a look at how 2 to the power of x, 3 to the power of x, and 4 to the power of x can be different, and how it also is the same because we're dealing with exponential functions. 2 to the power of 0. Let's do that first. 1. 2 to the power of 1. 2. And 2 to the power of 2. 4. And if you have these numbers, you can do the negative exponents as well. 2 to the power of negative 1 is 1 over 2. And 2 to the power of negative 2 is 1 over 4. Just like our exercise just now. Could you repeat that with the other examples? 3 to the power of 0 is 1. 3 to the power of 1 is 3. And 3 to the power of 2 is 9. What are the other 5 blanks? Would you fill that in very quickly? I think you can do it easily. Use the pattern. See if you can identify that pattern and run with it. I think I'm going to do... Oh, wait. Okay, yeah, I'll wait. All right. It was Abby. Claire, can you finish this off? All 7 of them? No? No, Claire. Okay. 1 over 3. 1 over 9. These two numbers, right? Okay, and then this one with the 1. And then, yeah. Okay, so it's all just 1 over the negative exponent. Remember, it just means I've taken that number and I've put it under 1. It's the same idea. Okay, so clearing this, keep that on your notes. I have it sort of mentally in my head, and I'm going to use it to draw this out. Oh, geez. Don't have enough space on my drawing pad for this. Okay. And I think I'll need as much space as possible. Let's do it 2 boxes to be 1, 2 boxes to be 2, 2 boxes as 3, and so forth. But on the upside, it goes up to 16. So do I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13? That's okay. Let's do 1, 2, 3, 4, 5 and 6, 7 and 8, 9 and 10, 11, 12, 13, 14, and then 16 is somewhere up here. And of course, we got -1. Oh, sorry. 2 boxes on the left is -1. 2 boxes is -2, and 2 boxes is -3. Okay. 2 to the power of x. I'll start with the red. Anything to the power of 0 is 1. And then it's 1, 2, 2, 4, 3, 8. So it looks like a parabola that doesn't start at 0, 0. It looks like a parabola. But on the left side, what happens? When x is a -1, the y is 1 over 2, half. And then it becomes 1 over 4. And then 1 over 8. And then 1 over 16. What does it look like? It's slowly approaching a value of, yeah. An exponential function has an asymptote. Okay, so this is 2 to the power of x, and it's got an asymptote at y equals 0. It's got an asymptote there. Okay. I will use blue for the 3 to the power of x. When x equals 0, the y value is a 1. When x equals 1, I have 3. When x equals 2, I have 9. When x equals 3, I have 27. That's way too high. When x equals -1, I have 1 over 3. When x equals -2, I have 1 over 9. So it's much lower than the red. So let me see if I could do justice to this. The blue is under the red, but then it shoots over the red when it gets to the positive side. Does that make sense to people? Right? I'm constantly multiplying by a 3, so it makes sense that I get bigger faster. But here, I am dividing by a 3, so it makes sense that I'm getting smaller faster. What's next? 4. If you're following the pattern, you'd probably be able to guess it. When 4 to the power of 0 is still 0. 4 to the power of 1 is here. And 4 to the power of 2 is 16. So the green line is under the blue line. It gets smaller faster. It also gets bigger faster. What is common between all of them? Just one thing. Just one thing. What is a general similarity and general differences for exponential functions? Go ahead, Josh. Yes. So the word I'm going to say it grows faster. It will also, the special word is decay faster, and you'll see why. Okay, it's true. Based on the base value. What is the common point? Yep. The y-intercept. Okay. Unless something funky happens to the exponential function, all base or all parent functions for exponential will always intersect or always go through the point 0, 1. Because anything to the power of 0 is 1. Now we get to something interesting, even for an exponential function. Remember how I said if you have a negative exponent, you just sort of flip it? If you look at this back of the first page, we're going to test it. We're going to test that idea. It's clear? All right. Let's compare these two graphs. We're going to draw the parent function first, but anyways, take a look. So if we have anything to the power of 0, the answer is 1, of course. And let's go through the negatives first. What is 2 to the power of negative 1? It's the same as 2 to the power of positive 1. That's a 2. And 2 to the power of negative 2 is like positive 2. So this is 4. What do you think that makes these values? Go ahead, Abby. Yes. Exactly. So let's draw that in. Here we go. Very quickly, I know that this is my parent function. It's going to look something like this. Okay. And now I am going to plot these new points. X 0, 1, 1/2, 2 quarter, negative 1, 2, and negative 2, 4. It's the mirror. Does that make sense? Transformation wise, what would that value be? What's happening to the x? It's being multiplied by it's not a trick question. The x here is being multiplied by a negative 1. It's the x value that's being multiplied by a negative 1. So is that a vertical reflection or a horizontal reflection? The x, it's the k value. X is being multiplied by negative 1. So even transformation wise, it makes sense that we are reflecting on the y-axis. Okay, so let's say you don't want to do this. That's okay. It follows the same AKDC system. You don't have to memorize it. Okay, but the reason why I want to show you this is because it's something interesting that happens when we have a base function, a base that's a fraction. You ready? I'll use red. Anything to the power of 0 is going to be 1. What is half to the power of 1? So anything to the power of 1 is itself, so it's just half. What is half to the power of 2? 1 over 2 times 1 over 2, it is 1 over 4. In the same way, half to the power of negative 1 is like saying positive 1 if we do the reciprocal. 2. Half to the power of 2 is 4. I think you notice that it's one and the same as the one on the left side. So my parent function would be bam, bam, bam. And in red, negative 2, 4. Negative 1, 2, 2, half, quarter. In other words, 2 to the power of negative x is the same as half to the power of x. Again, this sheet is just for you to see a connection or just some different properties of exponential functions to better navigate so that when you see a graph or when you see an equation, you know exactly what it looks like. You know exactly what the equation will be. As a quick extend, so take a look at these two graphs. Which kind of graph do you think can help model a growing trend, an exponential growth? What will be common for an exponential growth function? Okay, it would probably be positive exponent. What about the base? No fraction. That's right. With a, I guess, base value larger than 1, right? Because we need to continue multiplying the base value, right? If x is equal, so the exponent is 1, exponent is 2, exponent is 3, you have to keep on multiplying that number. So if you keep on multiplying by like a 0.5, the number gets smaller and smaller and smaller. You got to multiply by a number larger than 5, larger than 5. Anyways, is that my text? Anyways, okay. Next, which of the functions graphed could model an exponential decay or a continuing decrease, an exponential decrease? What is common for all exponential decay functions? Two conditions, right? One, it could be a base value greater than 1, larger than 1, greater than 1, plus a negative exponent. Or, and this is more typical, instead of using a negative exponent, right, we would use a positive exponent with a base value between 0 and 1. In other words, you might think of that as a fraction, a 1 over something. So an example of that would be something like, e.g., f of x is equal to, I don't know, 1, like 0.9 to the power of x. That would be considered a decrease. It would look like that, just like before. So keep that in mind. In my personal opinion, exponential functions is my favorite. And the reason being, the applications of it is almost endless in this world. There's a decent number of things in this world that follow a parabola, but there's even more that follow exponential, and it also overlaps the topic of money, which is really fun to calculate. So I like learning about this, and I like sort of teaching this because it sort of opens that up. Not only that, there's a lot of other examples like bacteria. There's a lot of examples like, here's an easy application. Everyone here, who here likes those? Like 5 years ago, there was this big fad of zombie movies, like 10 years ago. You know, like 28 Days Later, World War Z, and there's always been zombie movies, right? And even Netflix, there's what is it called? There's that Netflix thing where no, oh shoot, what was it? Like Gwyneth Paltrow was in it and she died because that's how it started. So you guys know what I'm talking about? Gwyneth Paltrow was there. The guy that played Morpheus in Matrix, Lawrence Fishburne. Yeah, he was in there. He was like one of the science medical specialists who was trying to contain the thing. Jude Law was in there. No, it was like a movie thing about, yes, either pandemic. Yeah. So it's basically any kind of thing like that is where exponential functions are used to model whether this is going to be contained or not, whether we're going to die or we get the vaccine. It's stuff like that. Um, money increasing or decreasing. Talking about the application of this into cars, why buying a car is such a common thing, but why buying a car is such a waste of money. So everyone here, if you're planning to buy a car, you're basically planning to throw away money. That's basically what was saying. Sorry, Jose. I know you like cars, but it is what it is. Okay. It's really fun. So I'm going to stop right there, getting you to sort of absorb all this. And then how about we go for a walk and then we'll restart at 11:15. Yeah. So finish this off. I'm going to send us out in about a minute. So right now you might want to just collect your stuff, make sure you have a jacket and stuff like that. Same with the people here.